For the Data for Good seminar that is a seminar series of the Columbia Data Science Institute. And today's seminar is being co-hosted also by Barnard Computer Science. I'm Rebecca Wright. I am both Director of Computer Science at Barnard and also Chair of the Data Science Institute's Cybersecurity Research Center. And we are delighted to have with us today Mayank Varia from Boston University, who really works in the area of applying cryptography and understanding cryptography in the context of real-world applications with real privacy needs and how it intersects with society and social good and the law. His talk today is entitled Data Science Without Data, and it will become clear throughout his talk why that is and sort of how that apparent conundrum can be resolved. So he is an associate professor in the Faculty of Computing and Data Sciences at Boston University. He also serves as the Director of Undergraduate Studies and the Civic Tech Hub Director. His research explores the computational and societal social aspects of cryptography, and his work has been featured in media outlets like CNET, The Hill, and ZDNet. And so he's got this sort of body of really interesting work that he's telling us about some of that is, as I said, uses cryptography, but also sort of thinks about cryptography and allows things like the equitable, accessible, and socially responsible use of data analysis for things like determining the gender wage gap, subcontracting to minority-owned businesses, and identifying repeat offenders of sexual assault inspired by the Me Too movement. All three of which are examples where the underlying data is sensitive or can be sensitive and has privacy constraints, and the solutions are the desired solutions should enable the necessary analysis of this data while respecting those privacy constraints. And he serves on the United States Advisory Committee on Data for Evidence Building, as well as the United Nations Privacy Preserving Techniques Task Team to promote the use of cryptographically protected data analysis, as well as shaping the laws and policies surrounding its use. And he received his PhD in mathematics from MIT in 2010. And Mayank, I will turn the floor over to you.
Okay. Thank you very much, Rebecca, for the very nice introduction. I am just trying to screen share. Can you see the presentation?
Yep.
Okay, great. So thanks everyone for inviting me to this great opportunity to speak at your seminar series. I'm excited about it. I want to talk to you today about the field of research that I do, cryptography, and how it connects to data science and society more generally. So I think of cryptography as something that's a social science at its core that's masquerading as a mathematical one. The goal of cryptography at its core is about helping people and companies and organizations to get things done in the digital world when they're concerned that someone else out there, somewhere on the internet, is out to ruin their day or worse. The biggest success story in cryptography so far is the widespread use of encryption. And I'll very quickly describe encryption, but I'll describe it in sort of a different way as a story about power, or maybe a story about the lack of power. And the punchline about encryption is that it shows that it can be both possible and empowering not to have other people's data. So encryption works as follows. Suppose that somebody, Alice here, wants to send a message, M, to Bob. Along the way, if she sends this message across the commercial internet, it will first traverse through telecommunication companies, through cloud technology providers, and through governments, ours or others. In other words, it passes through basically the most powerful organizations in the world. And even when faced against all of that power, the cool thing about encryption is it just uses some relatively simple math in order to allow Alice and Bob to talk to each other privately. And they do so by encoding their messages in a special way that only they can understand. And it works because even though all those entities in the middle of my slide have all this power that Alice and Bob don't, there is like one thing in the world that Alice and Bob do have that the other powerful entities don't. And we call this like a short string called a cryptographic key that is necessary to decrypt these messages. So in this way, as cryptographer Phil Rogaway puts it, crypto rearranges the power dynamics on this slide. Encryption alone has a weakness, which is typically you have to decrypt data before you can use it to do anything meaningful. And this leads to a tension when organizations deal with sensitive data. So on the one hand, there's this awesome rise of big data and the accompanying advances in algorithms to process it, and those offer incredible opportunities to improve society. But at the same time, everybody has become more cautious about data sharing over the years, precisely because things like data breaches can cause personal, financial, legal, and political harms. So let me discuss a concrete application where encryption alone won't cut it. And we actually need to go a little bit further, not just to protect data in transit across the internet as it flows across a wire, but actually protect data even as we're computing over it. And the example I'm going to give you is a real thing that we've been doing for the past 8 years. So several of us at Boston University have worked together with the city of Boston to measure the gender and racial wage gap using real salary data, measuring about 1 in 6 employees in the greater Boston workforce. And we're going to do this all without the need to share payroll data. So the work that I'm going to describe, we've done in consultation with a group called the Boston Women's Workforce Council. They're a public-private partnership. They're a group that's dedicated to eliminating the gender and racial wage gap. They do all sorts of amazing things that I won't have time to, I would have to give another talk entirely about all the cool and amazing work that they do. But for the purpose of this talk, one of the goals of what they've done is they've gotten about 250 or so companies across the Boston area to sign a pledge. And this pledge, among other things, includes a measurement component. It basically says that all of the employers in the city should jointly overall compute what is the overall citywide wage gap between men and women, and what is the wage gap across gender and ethnicity. And we want to do this every 1 to 2 years. And the goal is sort of under the mantra of what gets measured gets done. We want to do this in order to hold the city publicly accountable for moving as rapidly as possible to a world for 100% equal pay for equal work. Okay, and the text of that compact that these companies have signed, I put on the bottom left of the slide. And the text of this reveals this very careful challenge that there is there. So everybody agrees if you could compute the overall wage disparity across gender and race, everybody wants to know the answer to this question. However, the inputs into that calculation, the calculation itself is simple, it's just an average, but the inputs into that calculation are sensitive, they're people's salaries. And the challenge here is there a way for the Boston Women's Workforce Council to compute that citywide wage gap while at the same time keeping all of the employees and employers' salary data anonymous? So they initially tried to find someone who would be like a trusted third party, who would just be a data repository. Everyone would give their salaries to this one trusted third party. But the challenge is like nobody really wanted to do that. And also nobody wanted to serve as that data repository. Because think about it, if I asked you to do it, I'd ask you like, hey, please store all of the salary data for like 250 companies. And if you do happen to have that data breached, they will all get really mad at you. And when companies get mad at you, what I mean is that they will sue you all at the same time. This is not a very compelling role that you would probably want to take on. So let me show you concretely the portal that we have built for companies to submit their data into our system. You can go look at the website yourself. It's 100talent.org. The target audience for the portal, the people who actually use it, are the HR employees and diversity officers at the organizations who have signed on to this compact. And it looks like a normal web form. It looks like a spreadsheet. And at the top of the page, it's requesting some demographic information about the counts of the number of employees grouped by race, gender, and job category. The schema, the style of this format of the spreadsheet exactly follows the format of a form from the Equal Employment Opportunity Commission that all employers with more than 100 employees must complete annually. The point here is it's a format that the target audience is familiar with, and most of the compact signers already have this information available. So this is demographic information. If I go a little bit further down the page, we also ask for the same breakdown of gender, race, and job category. We also ask, what are the salaries that you provide to these people? Again, providing this, our goal is to measure this data as citywide aggregates in order to measure the overall pay gap and understand better its root causes. And if you scroll even further down the page, there's a few extra pieces about asking about performance bonus pay as separate from base salaries. Because in some sectors like finances, it can be a noticeable fraction of the overall salary that people make, and it can be determined through different organizational procedures, subject to different kinds of biases. And finally, we ask about employment duration, so we can perform this analysis based on how the salary data changes based on seniority. Okay, so far this looks like a typical website, but if it were a typical website, the way that this would work is after you type in all your data, the information would go to the person running the server, basically would go to me, right? But I don't want this data. I actually don't want it, and you probably wouldn't want to give it to me. So actually what's happening in this website is it does something very unusual and unorthodox for websites, that when you click on this submit button, the data itself doesn't actually go anywhere. So instead, what's going to happen is you're going to send some random gobbledygook to two different places, to me and the folks at BU and to the Women's Workforce Council. So how does this technology work? So this brings me to the cryptographic technology that I want to describe throughout this talk. It's a thing called secure multi-party computation, or NPC for short. And I'll describe how it works with the aid of this quote from a recent US Senate bill. So secure computation, or NPC, allows several participants to work together. These can be individuals, government agencies, or in our case, companies and nonprofit organizations across the city of Boston. I'll call them generically data holders. They're just people who possess some data set, such as their own salaries, but they want to keep their data private. They don't want to upload it into some kind of data repository. And jumping completely over to the other end of the pipeline, the data holders at the end of the day want to compute some function of their aggregate data, and they want to reveal the result either to one of them or to all of them or to somebody else. The function that they want to calculate, it could be a statistical analysis, could be a database query, a machine learning classifier, or anything else really. And the goal here is to get from point A to point B while along the way somehow keeping their data private. So this is kind of a form of data alchemy. We want to build a black box where you can put garbage into it and yet still have valuable data come out the other side. And to achieve this goal, rather than outsourcing their data to one trusted third party, I'm going to ask the data holders to split their data across multiple trusted third parties, or rather untrusted third parties. So it sounds weird. Rather than having one server to send the data to, I'm going to ask you to send it to 2 or 3. And the reason that it's going to be okay is that you're not going to send your actual data anywhere. You're going to first encode the data into pieces that I'll describe in a minute, and send the different encoded pieces to different servers, who I'll call the computing servers. Anyone can serve as a computing server, even those powerful telecommunications companies and cloud vendors and governments and whoever we saw from before. The data holders here don't have to know beforehand which one to trust. And in fact, they don't have to trust any one of them. The only rule involved here is that the data holders must trust that all of those computing parties are not collectively working together. That's because the way we'll design this is going to have the property that the computing parties together will have the ability to compute over and reconstruct functions of the data. But as long as they're not colluding together, we can mathematically prove that no one learns anything beyond whatever the desired output of the protocol is. And I'll describe how this technology works in more detail in a second, but the punchline here for the moment is that these tools allow the most computationally powerful and technologically savvy entities in the picture also to be the least trusted parties in the picture, which is pretty cool and pretty much the opposite of how the way that data science works today. So one quick caveat before we continue. So while MPC protects all the inputs and intermediate state in the calculation, it does reveal the output of the calculation. That's the whole goal. You want to learn, for example, the citywide pay gap. And as a result, it will also reveal anything else that can be inferred from the output. When I say inference, I mean in the Bayesian sense. So I'm not going to discuss sort of these kinds of inference concerns today. That's a separate question for disclosure limitation tools that, such as differential privacy, which you might have heard of. The good news is that these kinds of techniques are symbiotic. You can apply a disclosure limitation tool as well, and that will protect the output to make sure that the output is something you want to reveal. And you can also use the secure multi-party computation technology to protect the process of getting from the input to the output. Okay, so in this talk, I'm going to describe 3 applications of modern cryptographic tools like MPC. The first is I'm going to finish the story that I already started about computing the gender and racial wage gap in the city of Boston. The second thing I'll describe is how we've been building a system that can securely match sexual assault reports in order to determine repeat offenders of sexual assault. And the third thing that I'll describe is how to notify people whether they've come into close contact with someone who has tested positive for COVID-19. Okay, so let me start by talking about continuing on this question of what we've worked with the city of Boston on computing the gender wage gap. I'll show you how the technology works in a minute, but first let me show you why I think something like this secure multi-party computation technology is helpful. So one reason why I believe we've been successful in working with the city for the past several years is that we've purposely designed our system to provide value to everybody involved throughout our data analysis process. Right? So there's a bunch of different groups that are involved. So for example, the technologists and IT staff at the participating institutions, the questions that they would ask is, well, can you show us that whatever your technology is going to do, show us that it actually does what you say it will, that it's not behind the scenes secretly collecting all of our information and sending it off to Mayank's personal laptop, right? So they're asking questions about comprehension, transparency, and auditability. And one of the most useful features about secure multi-party computation is that it's very simple to describe, as I'll show you in just a few minutes. And we also made all of our source code available for anyone to look at. And it's small enough that it's actually feasible for people to check that it's working correctly and doing what we say. The lawyers that we spoke to were mostly concerned with questions about liability and non-disclosure agreements. I could give an entire alternate lecture just about that, but let me just put this issue aside for now, these kinds of legal considerations. But there are also things that we had to address. And one of the reasons we were able to address the questions about liability is because the goal of this technology is that we don't actually learn people's data in the first place. So our partners at the Boston Women's Workforce Council, their main goal was to get accurate, error-free data that represented a large fraction of the Boston area workforce. And using secure computation here turned out to be quicker, cheaper, and safer than finding a trusted third party to be able to hold on to the data in the clear. And finally, the human resources employees and diversity officers who actually use the system, their goal was just to have an accessible and simple experience so that they could type in their company's payroll data and move on with their lives. So in order to support these goals of accessibility and reducing errors, we built that website that I told you about before, 100talent.org, and we collaborated with human factors experts to design an easy-to-use website containing a normal web form in a format that the target audience was already familiar with. But behind the scenes, if you look at the JavaScript on this website, it has two special features. First, in your own web browser, there will be a proactive check for common types of data entry error so that it proactively warns an employee if they're about to before they hit the submit button, if the data looks anomalous. And the reason for doing this on the client side, where the client already knows their own data, is because it's going to be harder to do it afterward because we won't see their data, so we can't correct it in post-processing. And the second thing that happens with this website is that this site acts very differently after the employee hits the submit button. And the goal here is that the data itself doesn't actually go anywhere. So I said before that this system is easy to explain, so let me show you how it works. So to make things fit on the slide, I'm going to consider a scaled down version of the wage gap project, where let's say there's only two data holders, so two HR employees at two companies that I've shown on the slide, and let's say they have, and there's three different computing parties in my picture, and let's zoom in on one of the cells of the spreadsheet. So this first cell happens to ask for the number of female Latina executives at each individual company. Let's call the employer's individual answers to this question A and B respectively. And so our goal here is to build a system such that the Women's Workforce Council should only learn the sum of those two numbers, should learn A plus B, and everyone else involved in the picture should learn absolutely nothing. So to accomplish this goal, each company is going to split their data into pieces that are useless individually and only valuable collectively. And when I say these pieces, I'm really just going to mean numbers that are chosen uniformly at random, subject to the constraint that they add up to the company's real secret. So A1 plus A2 plus A3 equals the real party's answer A. Okay, and so each of the companies is going to send one piece of their secret to each of those three computing parties. So if you look at it from the perspective of a single computing party, they've learned nothing in this process because all they hold is a random number. And yet I claim that the computing parties can work together to compute the sum A plus B. And that's because that's the sum of all six numbers that I've drawn a box around. And remember that addition is commutative. So it doesn't matter if we first add the numbers vertically and then horizontally or in the other direction. And doing it in the other direction is more powerful here from a privacy perspective. So we can ask each of the computing parties, the red, blue, and green ones, to add the two numbers that it holds and to give just that result to the Boston Women's Workforce Council. And on the right panel of the slide, each of these numbers individually also has is also randomly, it looks like random gobbledygook, and doesn't reveal anything about A or B individually. So it preserves the data holder's privacy. But even though it doesn't reveal A or B individually, it does allow the Women's Workforce Council to find the sum A plus B. And that's because it can just add together the three numbers that I have highlighted here. And this is effectively exactly what our web-based software is doing behind the scenes. It just does so for more than 100 participating employers and for each of the 600 plus cells in the spreadsheet that I showed you before. So let's try something else. Even though it isn't required in the pay equity project, let's try something a little bit more complicated. Suppose we wanted to take the product of A and B instead. This is a little bit more complicated. We can't play the same trick as before and have each computing party just multiply its pieces because the math of that doesn't work. Instead, the product of A times B, you have to do, apply the distributive law, and it will become this more complicated expression on the right side of the slide, right? There's 9 terms to calculate here, and the computing parties don't have the ability to play the trick from before. They don't have enough data to compute most of the terms on the right side of this slide. But that's okay. I can solve this problem by making a small change to the protocol. So suppose that the HR employees gave 2 pieces of their secret to each of the computing parties in the way that I've shown on the slide now. This is still private from the perspective of any individual computing party. They don't know the third and final piece. So from their perspective, they just have 2 random looking numbers. And with this tweak, the nice thing is that there's at least one computing party that has the ability to compute each of the terms on the right side of the slide, which I've shown with my color coding. And these color coding pieces are the new encoded pieces that sum to the target value, in this case, the product of A and B. Okay, so, and that's basically it. Like, while I'm skipping a few low-level details here, this is like 90% of the way toward a workable method for doing secure multi-party computation that supports both addition and multiplication. And the nice thing about supporting both of those 2 operations is together that they satisfy something called Turing completeness, which is a fancy way of saying it's possible in principle to build any kind of computer program, any kind of calculation out of a bunch of additions and multiplications. But just because that's possible, that doesn't mean it's necessarily the best way to proceed. So in the remainder of the talk, I'm going to give 2 examples of custom protocols that also do this idea of secure multi-party computation. They can safeguard information, but in specifics that are customized to specific scenarios that involve sensitive data. Okay, so my next application is a project that I've been working on together with other cryptographers for the past 4 years, working with a nonprofit organization called Callisto. They're dedicated to helping survivors of sexual assault on college campuses. So universities are required by Title IX to provide systems for survivors of to report instances of sexual assault. But making a public report can be traumatizing for survivors. They might be scared about coming forward. They might be concerned about not being believed or fearful of retaliatory actions by offenders. So inspired by the Me Too movement, Callisto envisioned a new kind of system that would allow multiple survivors of a repeat sexual offender to be matched together so that they can act with a stronger voice. So I've collaborated extensively with Callisto to design a matching system that has the following workflow. So a survivor can log into the system and report the name of their offender. And later on, a lawyer will learn if and only if 2 people have named the same offender. And under attorney-client privilege, the lawyer can then contact the survivors and have a discussion about possible next steps. The most important part of the picture here is what's not revealed, that no information is revealed to the lawyer until a match occurs, and no information is revealed to Callisto, the organization that sets up this procedure, ever throughout this entire process. So all 3 of these steps of login, reporting, and finding a match are delicate due to the extreme sensitivity of the information involved. In fact, the login step actually might be the trickiest step of them all, because unlike a normal login system, it's important here that even Callisto itself has no idea who's logging into their service, because even knowing that a particular person is logging into this service is very sensitive information. Like there's only a few reasons why someone might want to log into this service. But in this talk, I'm going to skip the login step and focus on the reporting and matching pieces. It turns out that building a secure login system can be implemented using a more complicated version of the same basic building blocks that I'm about to show. So okay, once login happens, here's how reporting works. So imagine for the moment that there's this very strange black box, and it will work in this following way, that if you send into this black box the name of a person, of your claimed offender, it will return the coefficients of a line, like an actual line in 2-dimensional space, like in geometry class, as a response. So I recognize that, as shown on the slide, this black box is a really bad system because it's going to learn the name of an offender, and that's terrible. But it turns out this is a problem we can fix using standard public key cryptography in order to build a new kind of box that will work in exactly the same way, but without ever learning the offender's name. So I'm going to skip the details about that in the interest of time. Let's just assume that the black box can work in its way without learning the offender's name in the process. But like, why do we even want this black box? This very strange thing. So in this particular example, Alice has submitted the name of her offender, Zeus, and she receives back in response this blue line. And then what Alice is going to do with this is submit two things into the lawyer's database. First, a randomly chosen point on that line, and second, an encryption of her assault report detailing her accusations, her experiences. And the encryption key that she uses for this encrypted report is the y-intercept of the blue line. Okay, so on its own, this information is useless to the lawyer because, the lawyer just sees this one point that is not the y-intercept, not the point with the key. And from this one point, there's many lines that go through Alice's point, and the lawyer has no hope of recovering the correct key and decrypting the report. Okay, so on its own, so far this is useless, but suppose there's another person who comes next, Bob, and suppose he names the same offender Zeus. The box has the property that it's deterministic. So that means if two people name the same offender, they will receive the exact same line. So Bob will receive the same blue line that Alice happened to receive in the past. He then does the same process. He sends the lawyer his own randomly chosen point on the line together with his encrypted report. The important thing to remember here is that the line itself is determined entirely by the name of the offender, whereas the points chosen from the line are chosen independently by each survivor and are therefore unlikely to collide. And because 2 points uniquely identify a line, now the Callisto lawyer has enough information. They can interpolate the line, recover the blue key, decrypt Alice and Bob's reports, realize that a match has occurred, and begin an investigation accordingly. Okay, let's do this one more time. Suppose there's another person who comes, Carol, and she names a different offender, Poseidon in this case. Then the box is going to give her a different line. Let's say this orange one. She'll do the exact same procedure as before. She'll submit a randomly chosen point on the line together with an encryption of her report of her experiences. This time, though, using the orange key, the y-intercept of the orange line. Because the lawyer only has 1 point on the orange line, there isn't enough information in the system still for the lawyer to reveal Carol's record. And that's true even though the prior reports have been submitted by Alice and Bob. They don't help the lawyer because the orange line is chosen independently from the blue line from before. That's another feature of the way that the black box works. And so if the lawyer tries to match Carol's point with Alice's or Bob's, this is incoherent. This will result in the wrong key and Alice's record will be protected. It will not decrypt. And so that's basically it. With this kind of black box, we're able to build a system that allows survivors to report instances of sexual assault, and that if and only if a match occurs, then a lawyer will be notified. And the lawyer can then work with them to talk through whatever their appropriate next steps are. So the full system that we've built working with Callisto has a few extra features and optimizations beyond what I've actually shown here, but the punchline remains the same. The goal here is the lawyer cannot read any report unless 2 people name the same offender, and Callisto itself never learns anything throughout the entire process. Okay, so in the third and final part of this talk, I want to talk a bit about exposure notification programs that exist on smartphones. You might have seen one of these depending on the state that you live in. So I want to talk about the work that I did as like one part of one team. A lot of people looked at this problem a couple years ago. There have been many teams who've been looking at the design and analysis of electronic exposure notification schemes for smartphones, wearables, and other kinds of devices. And the goal is to inform people if they come into close proximity with someone who later test positive for COVID-19, but in a way that you never store anybody's health history or anybody's location history. And the goal here is to complement contact tracing by public health authorities, which is a time-tested strategy to reduce infection during pandemics. So we're all probably very familiar with everything related to COVID-19 and public health reports, but public health strategies. But just to recap how contact tracing works, the idea here is suppose there's a person, Alice, who becomes infected with COVID-19 and later infects Bob. So because Alice becomes symptomatic before Bob even becomes infectious, and therefore Alice might even get tested before Bob even becomes infectious, the idea is for Alice, or really a public health authority, to tell Bob so that he can quarantine before he even realized he had COVID-19, so that we can cut the chain and he will not infect his friend Carol. So this strategy is amazingly effective when people can tell health authorities about their contacts, but that doesn't always work because not all of the people will remember all of the contacts that they've come into all the people they've come into contact with. They might not be willing to share all of their contacts with the public health authority. The public health authority might be overwhelmed with a surge and may not be able to have enough staff to communicate with everyone. So the goal here is to have an electronic system that can complement the contact tracing system and also provide an indicator about the possibility of close contacts. Okay, so in 2020, I contributed to, like I said, one of several teams that looked at this question and showed how we can build an electronic notification system. The goal here is to tell people when they come into close proximity with someone who's later diagnosed with COVID-19, but without storing anybody's health or location history. So at a high level, here's how the system works. It's a thing that's likely, depending on the state you live in, something you can download today or available within either your operating system or your app store for your phone. And the way that it works is if you enable this, then your phone will start sending out random numbers, completely random numbers that we call chirps. It will send this out over short range Bluetooth radio so that only other phones that are within close proximity of yours can hear them. So in this picture, Alice is going to send a chirp and Bob's device will receive and record this chirp for later use. It's a totally random number, and at this moment, it doesn't mean anything to Bob yet. It doesn't say Alice's name. It doesn't say the location that they're at. It says nothing like this. Okay, behind the scenes, it turns out that the chirps were a function of a secret that only Alice knows. But as far as anyone else is concerned, the chirps look like random strings, and nobody can associate them with Alice's identity. If Alice is later diagnosed and tests positive for COVID-19, she can submit some function of her chirps to a server. I write this as some generic function F of the secret, but for now, let's just think of F as like literally sending the secret itself, although other choices are possible. And then Bob can then later download the contents of the server and match them against his own chirps. So basically, the server contains every chirp that was sent by people who later tested positive for COVID-19, and other phones locally know all the chirps that they have heard. And if they see a match between the random numbers on the server of what people who were COVID positive have sent versus what they've received, then here Bob will know that he's a close contact of someone who's tested positive, and he can quarantine accordingly. So this would have worked actually just fine if we just submitted the chirps to the server itself. The main benefit of having this thing where there's this secret, this like indirection between this initial secret and the chirp, is that we can use cryptographic techniques to make it so that we can provide stronger integrity. And what I mean by that is we can design this function H, that the way that the chirp is derived from the secret, to be something called a one-way function, that you can compute it in the forward direction, but it's impossible or very, very difficult to compute in the backward direction. And as a result, anybody who submits this secret, this pre-image of this chirp to the database, at this point, Bob will know that he's communicating with somebody who's the actual Alice. Not communicating with, he's receiving a message through the server from the actual Alice who actually sent this along, rather than just some other bystander who happened to hear the chirp along the way as well. So the system here is symbiotic with manual contact tracing, and the goal here is to help fill in those missing links, like the stranger on the subway. It also respects people's autonomy over whether and when to participate. But even for such a simple system, the choice of which functions H, of which function to send in, what to send in a chirp, and F of what to send to this untrusted server, these choices are subtle. And we have an entire paper analyzing several choices of these options and showing how many of them can provide both strong confidentiality, meaning that attackers cannot learn people's location and movements over time, cannot learn their health statuses, and cannot learn, and the system also provides strong integrity, meaning that an attacker cannot upload data to the server in order to like scare people that in reality they've never been in close contact with. We also looked at a lot of different security concerns, such as, for example, limiting the damage done to privacy if someone happens to hack into your phone and exfiltrate either those secrets or the chirps. So those were 3 different examples of this technology of how to work with data you cannot see. And I think sort of the punchline here of this talk, and really of this technology in general, is that using cryptography, it allows us to do data science in this brand new way. That's why I called this talk, the title was Data Science Without Data. That the nice thing about this technology is it allows us to figure out ways to derive knowledge that does have social value, to derive that knowledge from data, that real data sources, some inputs of arbitrary inputs x1 through xn, without requiring those data holders who have that sensitive data to share it or to trust anyone else. We can recover the knowledge without sharing the data. And in this way, this concept of secure computation can really allow us to reimagine all sorts of concepts, like what does ownership of data mean? What does custody of data mean? Jurisdiction, disclosure, and liability in this information society. And so in closing, I'll just say sort of like, I really think this is a nice way to sort of like increase the Pareto frontier of what kinds of technologies, what kinds of data science analytics are possible. I'll close by describing in this report that I show a picture of on the screen. This is a report written in 2017 by the US Commission on Evidence-Based Policymaking, a group created by the US federal government. And they envisioned actually this new thing called a National Secure Data Service that they want, government agencies, federal, state, and local government agencies to be able to do exactly this, to be able to link their data sets and run statistical analyses on this joint data, but without storing the data in a central warehouse in the process, to be able to link data between cities or between states. And they have this picture that I really like, and I'll close on, that sort of talks about the concept of if we can decouple access to data, and we decouple having the need for having the data from the ability to gain insights from it. Secure multi-party computation here really expands the Pareto frontier of data analyses that can be performed. And it allows us to conduct data science in a new way that can simultaneously enhance the accuracy and quality of data analyses by getting us to more and better ground truth sources, while also at the same time respecting personal autonomy and consent and enforcing data minimization and purpose restrictions. So thank you.
Great. Thank you so much, Mayank, and everyone. Please join me in thanking Mayank, although you are virtual and we can't see you. But actually what we can see, and we do have time for, is some Q&A if you have questions that you'd like to raise. So you can put those in using the Q&A button that you should see at the bottom of your Zoom screen, and we can pick them out and respond to them here. And let's see, I guess I will start with a question while we see if there's any from the audience here. So you talked a little bit in the Boston Workforce Project about specifically with the IT coordinators, how you helped them to understand that this system was behaving differently than it might look like, right? So if these things are designed in a very usable way, they look sort of like systems you might use where you would actually be inputting and sending this information. And so I'm wondering maybe sort of a more general version of what you did with those IT people. So how can you help individual users, in something like Callisto, or the people at the company whose data is being shared in this private way? How can you help them to understand the difference and to feel comfortable and confident that that their data is not being put at risk?
Yeah, that's a really good question. So, I'll sort of answer it in a couple ways. One is one potential feature of this technology for people who are not thinking about this question is that it can all work seamlessly behind the scenes, right? So like from a usability perspective, for people who just want to sort of like have the workflow work in the normal way, the fact that we can build this, for example, in the Women's Workforce Council into an existing onto a web page, and it looks like an ordinary web page. There's nothing that screams of like, this is some new and complicated thing and you have to work in a very different workflow than you did before. So if you're not interested and curious and want to learn about the details of this technology, like my point is, at least from a usability perspective, it's no different than the way it works before. The fact that it's seamless behind the scenes is kind of nice, but for people who are interested in the details of this technology, it's a good question. I don't have a great answer other than to say that I think the system is simple enough to understand that we try to just describe it like a version of this presentation is the same kind of thing, like earlier versions of the same slides are basically the same thing that we have given to, in the case of the Women's Workforce Council, to HR employees, to lawyers at the companies, to C-suite executives at these companies. And it's relatively simple to understand. The idea of, okay, I just split a number into two pieces that are individually random, and it's relatively simple to understand. For the Callisto thing, the actual process is a little bit more complicated with this idea of this geometry and the lines and all. We do have a white paper that we posted. It's not too long, and I think it's, maybe I'll say it this way: relative to other kinds of cryptographic techniques that could exist to solve this problem, it's relatively understandable. I don't know how comforting that is, but it's our best faith attempt to build a system that can both be privacy protective and understandable. And also with the exposure notification thing, that was a huge consideration that went into the design of this. The idea of like, I'm just sending out, I turned your phone into a beacon. That sounds bad, but I'm only beaconing random garbage that has nothing to do with your identity, nothing to do with your location. And so every time you're beaconing, as you walk around, there are random numbers that are uncorrelated with the random numbers from 15 minutes ago. So it's not like someone can even track you and follow you over time by looking at this random number. And I think that idea is intuitive, even if the rest of the system of how the crypto of like how those functions F and H work get a little bit more complicated, admittedly. But the fact of sort of the simplicity of understanding that you're just like beaconing these random numbers that change all the time and can't be used to identify you, I think is relatively understandable.
Mm-hmm. And you intentionally skipped over sort of what you had to do with the lawyers. I'm curious if you can say a little bit more about that and how much they cared about understanding sort of the mathematics that data isn't flowing certain ways, or whether they were more interested in whether things were compliant with, relevant laws, or what kinds of privacy policies they had to have and state to their, I'm just curious sort of how that conversation was similar and how it was different from the one that you might have had with the IT managers.
Sure. I'll answer that in two pieces. First, what was the experience working with the lawyers on the Women's Workforce Council itself, and then the legal compliance question, which goes, I think, beyond just the Women's Workforce Council example. So for the BWWC work, the lawyers, for the most part, understood the technology pretty well, but the technology has a weakness, which I hope I was upfront about from the beginning, that if all of those computing parties work together, then they can reconstruct the data. So if BU, which has its one piece, the A1 and B1 and the Women's Workforce Council, if we pull our pieces together, we actually can reconstruct the data. And so for that, the lawyers at some of these companies insisted upon us signing a non-disclosure agreement, which we did. And the interesting thing I'll mention here is that this is also a strategy that previously to BU even being involved in the picture, and when the Women's Workforce Council first went to a trusted third party, they of course, if you're going to give all the salary data to a single entity, they would also insist upon a non-disclosure agreement, which is sensible. And as I said before, nobody was willing to take on the liability risk involved. And I think the interesting thing about this there's a mix of legal and technological constraints to protect the data, is what I'm trying to say, that the technology ensures that like no individual one of these servers has the data, and the law, the non-disclosure agreement, ensures that the two parties, can't work together, at least contractually are forbidden from working together. And it's a nice way to sort of have a symbiosis of these two pieces to sort of a defense in depth, if you will, of protecting data, and also making the in-house counsel at BU ultimately going up to, long story short, we ended up emailing the president of Boston University on a Saturday saying, you need to sign this agreement. And after he was like, what on earth are you crazy people doing? He did it. And part of the reason why he did it is because he and the general counsel's office did it, is because the fact of us not learning the data made them feel more comfortable signing it than perhaps one BU or any other organization would have felt if it was data shared in the clear. And then to your broader question about sort of legal compliance or consistency with data privacy laws, maybe is how I'll phrase it. It's a good question, and actually an interesting property of all three of the applications that I've said, as well as pretty much all of the applications of secure multi-party computation to date, is they involve data that people intuitively think of as sensitive, but is actually not covered under a US federal data privacy law. There's no law saying that companies can't reveal your salary. And in fact, there exist some companies where salaries are public knowledge, right? Similarly for the other types of data, there's no law saying that, it protects that protects the general public from knowing your COVID-19 infection status, but you might not want to share with the entire world exactly your health history. So it's kind of an interesting feature that it's an interesting phenomenon that all of the applications of secure multi-party computation use data that's actually not subject to data privacy laws. And I think we maybe should view this as a bad thing, that the data that we feel as the society is most sensitive, that we choose to build specific privacy laws to protect it, are the kind of data that you think would be most likely to benefit from technologies like this, but somehow aren't yet. And the conjecture that I have as to why that's happening is because of sort of the challenge of mapping the technology onto the law. If you're a lawyer who's tasked with figuring out, does this thing match with, suppose there's protected healthcare data involved and you run a hospital and you're saying, is this consistent with HIPAA? Or say they're university records and you run a university, is this consistent with FERPA? That's actually a pretty hard question to answer. There's this brand new technology that is, first of all, no one has analyzed it yet with respect to this law, so you'd be doing this from scratch. Second of all, the law is written in a very different way that doesn't even take into account the theoretical possibility of the existence of technologies like this. It was written for a very different kind of question about what kinds of data sharing or not are allowed or prohibited. So if I give you these secret shares of data, these little encoded pieces, does that count as data sharing or not? I have no idea. So one thing that we, together with folks at the BU Law School, have been working on for the past couple of years is exactly trying to build a framework or a way for lawyers to think about these questions when you have data that actually are subject to data privacy laws. How should you go about reasoning whether and in which cases the use of this technology is okay and consistent with the letter and the spirit of those laws? So I think that's a broader question that I'm super excited in and have some initial ideas on, but I left them out of this talk, sorry.
Yeah, no, I think it's really interesting too, and sort of exactly this question of on what basis could a lawyer say that something was okay to disclose when their whole job is to be super careful about that kind of question. So I think that is important. We have a couple questions coming in the Q&A, so I'll read them since I think you and I maybe can see them, but the other participants can't. So Lisa says, nice talk, thank you for the presentation. Quick question, what software is used to analyze these data to prepare a meaningful report that can be used to prevent future actions? For example, prevent COVID-19 exposure or catch the offender, et cetera.
It's a great question. So a lot of okay. So for the Women's Workforce Council example scenario, what we actually provide to the what our software provides to the city, to the Women's Workforce Council, is basically exactly the same spreadsheet as you saw at the very beginning of the talk of the number and salary of each demographic and each racial and gender and job category group, but across the whole city, rather than for any one employee or employer, across the whole city. So we provide, that's basically the data in the format that we provide to the Women's Workforce Council. And so it's already only citywide aggregates, but it's citywide aggregates for each of those cells in the spreadsheet. And what they do after the fact is convert it into an actual brochure that's easy for people to digest. So if you go to the bwwc.org, you can read the reports that they have. So we've run this pay equity exercise in 2015, 16, 17, 19, and 21, so 5 times. The first time it was like they decided not to publish a report because they were trying out this new technology and they weren't yet sure how well it would work, and it was sort of a pilot. But the other 4 instances of it, they have reports that are available online. But basically, we just provide them with that city level aggregate stuff, and then afterward, the rest of the sort of, I think the question is about data synthesis and visualization. None of that has changed. All of that is exactly the same as it would be for any other data science application. For the exposure notification work, which the development and integration of this has been led mostly by Apple and Google, smartphone vendors, together with some private companies who have built the applications to put in the App Store in different states and different countries. Different companies have built the applications that all follow the same basic premise that I said. And there the stated goal, the primary goal of this is just to provide information back to you as an individual smartphone owner about have you come into close contact with somebody else who later reported COVID, who later tested COVID positive. So there's no aggregate data, so to speak, from that. It's very personalized. But I didn't say it in the talk, but there's another system that Apple and Google have built that's I think is very neat, that basically allows you, using a different secure multi-party computation protocol, to provide to your state public health authority an aggregate metric of how many people across the state have reported being close contacts of people who've tested positive. So that way they can get, state public health agencies already know the results of people who actually tested positive. If I go today to get a COVID test and it tests positive, like if I go to the CVS down the street, the CVS is required to tell, in my case, the Massachusetts Department of Public Health about this test, but they don't know about the close contacts, right? And the nice thing about this other system that I didn't show in the talk is that information can also be aggregated using secure multi-party computation as well and provided to a state authority. And so in that case, yeah, they just learn these sort of like the sum of all these statistics across everybody, and then what they choose to do with it in terms of data visualization. Again, all of those questions are exactly the same as they would be for any data science application.
Great, thanks. And we have one more question in the Q&A, which is maybe a little broader than the topic of your talk, but I'll read it to you, and you can see if you have a way to answer it. So Francisco says, thank you for this interesting talk. I'd like to make a question. How would you define psychology in terms of AI? Do we need to conceive subjects as social agents not determined by a teleology construct for a purpose? Thanks. And I'll say maybe the potential connection here is sort of, how do we think about the autonomy of individuals and sort of their needs and constraints and desires, and how that interacts with technology? Maybe that gives a useful bridge to the question.
Yeah, it's a very challenging question, and the short answer is I don't know. But I think the rise of very powerful data science and machine learning and AI algorithms allows us to advance ourselves as a society, but we have to be very careful and clear about how to do so in a way that advances the interests of real, actual people, as opposed to AI algorithms and all. And hopefully one of the themes that I got through in the talk is about doing data science that has social benefits to people, and does so in a way that also respects the autonomy and choices and the free will of people to choose whether to collaborate. And I hope creates the incentives that people want to collaborate again, because they see that the result of a data analysis is actually socially beneficial, and that by protecting their privacy throughout the entire process of doing of performing a data analysis. It's something that spurs them to participate in ways that they might not have otherwise, but still, and also sort of allows people to have more, to participate in a data science application without the need to outsource their data to a repository where you then, it's much harder for you to have a say in how that data is used afterwards. So to have the ability to participate on an opt-in basis, on an individualized basis, that's sort of like where I think this technology is useful. The broader questions about the future of AI, I don't know. Those are great questions, and I'm not equipped to answer them. Sorry.
Yeah. Great. All right. Well, I think we will conclude here. So please virtually at least join me again in thanking Mayank Varia for this really interesting and informative talk. And thank you all for attending.
Thanks, everyone.
Thank you all. Bye.